All right, so today we're going to do the final review, and we're going through a list of topics. Okay. And he will do the first half, and then I'll do the second half. So starting right now.
Oh, so I have a question.
Oh, sure.
Yeah. Are we gonna have time to ask any questions today?
Yes.
Yeah, let's go. Yeah, thank you.
So I guess like while I'm lecturing, you can come up and actually ask her specific
Okay, it's
questions.
fine. Like he could like listen to what you're
Oh,
saying.
yeah.
Yeah, two.
Okay, yeah.
Yeah, I'm gonna pay attention, you know.
All right. We will start off with concurrency, just to review last week's material, and then afterwards we'll probably like get into data structures and review those before moving on to other topics. And so just to start, we have concurrency. Well,
Mhm. Okay.
Okay. So what we want is to be able actually to run parts of our program at the same time in parallel. In a sense, we're splitting our entire process into multiple threads of execution. And the reason we want to do this is because it gives us more responsive applications and also allows us to leverage like the power we get from multiple cores on our computer. You should note that for threads of the same process, threads will share memory. So for example, Java threads will be able to reference the same objects in memory, although they are given different call stacks for the same process. And concurrency introduces non-determinism in that the instructions of your threads can be run in many different orders. So there are many different interleavings of these instructions. And this can be problematic for debugging and designing, especially when you're trying to access a shared resource. In particular, we outlined this problem, this race conditions that might arise when threads try to essentially race to a shared resource, and at least one tries to update it. And so while some interleavings might be correct, there may be some interleavings that actually produce incorrect behavior. And so the example we provided during lecture was with the stack. So if we have, say, two threads that are trying to call this do something method, which basically checks if the stack is empty and then tries to pop the first element and do something with it, we can see that there's one interleaving in which the first thread tests whether the stack is empty and then pops, and then the second thread does the same. And when that second thread does it, and say there's only one element on the stack, it finds that the stack is actually empty and it can return. But there's also a different scenario where you have one element on the stack and the first thread tests if the stack is empty. And then the second thread also tests if the stack is empty. And this both returns false. So essentially both threads have the go-ahead to continue with the method. However, when we move on, the first thread will pop, making the stack empty. And then when the second thread tries to do the same, it will run into an exception because the stack, well, is now empty. So all it really takes is one bad interleaving. And the problem is not every run you make with this with these two threads will result in this exception. So it can be hard to catch. And so we want to have some way of preventing this. And we do this through something called mutual exclusion, which is basically the idea that there are blocks of code that two threads should never run at the same time, essentially. So for the previous example, our critical section that we want to prevent threads from running at the same time is essentially this method body, right? If one thread tries to enter that, we want any other threads to be unable to run that at the same time. And one simple way of doing this is with locks. So one thread can take a lock, essentially just preventing from any other threads from entering that same kind of code section, and then release the lock when that thread is done. In Java, we're given synchronized blocks to help us enforce mutual exclusion. So essentially, these are you can think of these as kind of locks associated with some given object. So with this synchronized block, the syntax is you write synchronized and you specify an object to synchronize upon. And so if any other synchronized thread tries to access your object, you'll have a lock on it, essentially. And this is syntactic sugar. That is, it's equivalent to just writing synchronized in this method signature, the
Yes,
method.
sir, I have a question.
Yeah.
Yep, for the synchronized, if we just synchronize this object and we have another method, it's not synchronized, then would that method be able to edit the build variable?
I believe it should be able to, yes.
Oh, really?
Yeah.
So if we just only add one synchronized, so it's kind of like useless, right?
Yeah, I mean, there are instances where you might want to synchronize on one object. So like have some threads synchronize on that one object, but other threads can actually run concurrently on that object.
Oh,
right.
Okay.
That's why, yeah.
Oh. So when you change that, if you try to use the object in that context.
Yeah, with the synchronized block in it. Yeah. Okay, and so we'll diverge to the bounded buffer problem because you do have to be somewhat familiar with it on your final. So a bounded buffer you can think of as just a bounded queue, a queue with limited amount of entries. And so the operations on your bounded buffer, well, we have producers and consumers. Producers put items onto the buffer and consumers retrieve items. And the implementation you should probably be familiar with is the array queue implementation we showed in lecture, right? So this is essentially having a backing array, and then we'll store like the head of the queue at some index and also the tail at another. And then we'll essentially just be working with the queue like with wraparound on the array. And so although you don't have to know like the notify and notify all stuff for your final, you should be familiar with like the race conditions that can arise. So like if you have two producers trying to access the same buffer, it might be the case that one producer fills up the buffer and the other tries to do the same, even though it's already full, some stuff like that. And then the other problem we have when dealing with concurrency is deadlock. So when we try to enforce mutual exclusion, so when we have something like locks, we also run into a problem where multiple threads will try to access multiple shared resources. So we'll try to grab multiple locks, essentially. And so what happens is each thread gains access to a resource that the other threads need to like continue. And to understand that, you could probably try looking at these images, right? So you have thread 1 and thread 2. Thread 1 grabs a lock to object 2, while thread 1 grabs a lock to object 1, and thread 2 grabs a lock to object 1 and object 2. But thread 1 actually needs to access object 2 to continue, and vice versa for thread 2. And you can see that now no thread can actually make progress. And same thing here with your dining philosophers example. If Einstein here grabs the knife, and then the thinking man grabs the fork, but these philosophers need both utensils to proceed, then we see that nobody can actually start eating. So yes, that will be concurrency. As for anonymous functions, I guess I can cover this now. So anonymous functions, so these are just functions that we don't assign to any identifiers, any variables. The syntax for this, so if you have a single line, you can basically just condense it down to this form where you specify the arguments, the parameters here, and then you have this arrow, and this single line will just be the return value for your anonymous function. Whereas for multi-lines, same thing, you have your parameters, but now you specify a block of code, right? Where you can have multiple lines. And here you do need to actually specify returns because it's not a single line anymore. And so this is useful because we can actually pass anonymous functions as arguments to other methods. But I guess the confusing thing is, well, how does the Java compiler actually know the type of any of these anonymous functions that we pass in? Like here, we don't specify any, specify any types for our anonymous function, right? Well, the answer is it's because of the functional interfaces that we define. So going back to GUIs, if you recall, we have something called an action listener. So this is an interface that essentially just defines one abstract method. And these interfaces we call functional interfaces. So now any method that has a parameter of type action listener, we can actually pass in an anonymous function as an argument, as long as, say, like the return types match up. What happens is the type of the anonymous function is essentially just inferred from the functional interface that's specified where you're using this anonymous function. So in this example, you have a J label and a J button, and you're attaching an action listener to this button 1. And essentially what happens is, since you're passing it into here, into this method, which takes in a parameter of type action listener, this will be cast as, or the type will be an action listener essentially. And it can infer the type of this anonymous function from the method defined up here.
Do you have a question?
Oh, yeah.
Threads can also take anonymous functions, right?
Sorry?
Threads can also take anonymous functions. That's part of the
Sorry, could you repeat that?
So I think the thread objects also take anonymous functions as arguments.
Yes, they can take runnables, right?
Threads. Yeah, I think.
I
as
believe
argument.
so. Sorry?
Yeah, it can interface.
Yeah. So yeah, they can take a runnable as an argument, so you can pass in an anonymous function. Yeah. So yes. Yes, I wanted to review this test question, just to drive home the points of the functional interface or the distinction. On test 5, we gave you this interface essentially that has 2 abstract methods defined. And we asked you whether we can actually pass an anonymous function wherever we take in a parameter of type window focused listener up here. And the answer is no, because this is not a functional interface. It takes in 2 abstract methods instead of 1. Even though this is pretty similar to the GUI stuff. It is an interface. It's not a functional interface because a functional interface can only have 1 abstract method specified. Yeah. Loop invariance. So our loop invariance, we start off with our 4 loopy questions. Essentially, our first one is, does it start right? So we want to be able to ensure that our code for initialization truthifies our invariant. 2, does it stop right? So we want that if our loop terminates, essentially when not B holds, along with our invariants. Does this truthify our post condition? And 3 is whether our repetend in the loop makes progress towards termination. So like if we're maybe incrementing and our loop condition checks if our counter is of a certain size or something. For 4, does repetend S keep invariant P true? So is the invariant basically preserved with each iteration of the loop? This might be somewhat hard to parse at first, but you should know, at least you should be able to give us like the 4 loopy questions on the final. As for the types of questions you might encounter for, if you're given like a precondition, invariant, and post condition, we'll probably want you to initialize so you can truthify the invariant from the precondition. We want you to be able to write a loop condition so that when you terminate, you also fulfill the post condition. And you have to be able to write a loop body that preserves the invariant. As for how to approach this, at least for initialization, you can think of it as like, take this example question from test 3. So you're given the precondition and the postcondition as well as the invariant. And the idea is basically, how can we set J and K, which are the index variables for our invariant, so that we can basically match this invariant with a precondition, right? And so the answer here is that, well, this question mark section should fill up the entire array at first. So initially J should be at 0 and K should be at b dot length. For loop termination, we want to consider like, for what values of J and K does the invariant match the post condition? For our post condition, we can see that this question mark, this unprocessed section is basically nothing. So everything has been sorted into evens and odds, right? And so this is when J is essentially equal to K. So that's the condition when you should terminate. So that will essentially give you not B, right? And so once you have not B, it's pretty simple to just negate that and get B, which is your loop condition. Before I get into searching and sorting, I am going to review big O. So big O is essentially like a mathematical tool that we use to provide asymptotic bounds. And what that means mathematically is that, well, we can say that a function f of n is in big O of some other function g of n, if and only if there is a positive constant c and a real number n such that f of n is less than this multiple of g and n for large n. And so what that basically means, you could probably just get the intuition from the graph, right? So for some large n past a certain point, we can see that f of n is bounded from above by some multiple of g of n. And this is pretty useful in computer science because it gives us a pretty great way of analyzing algorithms. So we use big O to classify algorithms by how they respond to changes in input size. So we use this to characterize both the runtime and like the space complexity. As for runtime complexity, the usual bounds we have are this constant time, logarithmic time, so like binary search, for example, linear time, so perhaps removing some arbitrary elements in a linked list, quadratic time. And so I think this was also a previous test question. Can an algorithm with runtime in O(n) squared be faster than one with runtime in O(n)?
I think it's yes.
Yeah, right. So one thing is that, well, O(n) squared actually might not be the tightest bound for your algorithm. It could be that the runtime is actually, say, log n, but that's still in O(n) squared. And even if these are the tightest bounds, big O is used to characterize asymptotic behavior. So like when your input sizes grow like to large values, right? So for smaller inputs, it could be the case that an algorithm with type bound O(n) squared actually runs faster than one with type bound O(n).
Do you have a question? I'm recording.
Yeah.
The Zoom. Yes, it is.
Yeah. Okay, so these are just some informal big O rules you might be able to use. So say you're like given some method with a loop in it, and you're asked to analyze the runtime. So we see that if we have a function that is in O of f of n and a function that is in O g and n, actually, it's best to contextualize this in probably a loop. So we can say that the number of iterations you make is perhaps in O of f of n, and each iteration takes time in O g of n. And generally, this rule applies where you can just kind of multiply the functions inside to get the overall runtime complexity. And when you have, say you're doing something sequentially, so you're running an algorithm, you're doing one step that runs in O of f of n, and then you do a second step that runs in O of g of n. You're essentially just adding these functions, right? The number of steps is essentially the sum of these, and you can just take the max of these to be your overall runtime. You should be able to prove that a given function is in big O of another function. So to give an example, we can let f of n be this 3n squared plus n, g of n be n squared. And so to be able to prove that f of n is in O of g of n, we want to find positive c and real n such that this holds. And this is just basically regurgitating the definition. You should be able to, which you should know. As for how to approach this proof from this, once you know what to prove, we should start with f of n. So the function we want to prove is in the big O. And the next step is we probably want to say that this is less than or equal to. We want to bound it from above by another function. And it's best if this other function has basically the same terms involved in like this g of n function, right? So here we can say that 3n squared plus n is less than or equal to 3n squared plus n squared for n greater than or equal to 1. And this is a good step to make because then we can just say that, well, f of n is less than or equal to 4n squared for n greater than or equal to 1. And this is essentially what we want, right? N squared is g of n, and this is a multiple of it. And so we have essentially bounded f of n by some multiple of g of n for n greater than 1. Any questions? Okay, so that is the proof. Probably we'll skip over this, though should be able to answer all of these as well as give the proofs. Okay. So some big O examples. What is the runtime of an algorithm that runs insertion sort on an array and then runs binary search on that now sorted array? Does anybody want to give this a try? O of log n. So first you run insertion sort, right? And insertion sort will run in O of n squared time, right? Oh, okay, yeah. So yeah, so it should be O of n squared because here the insertion sort kind of dominates the runtime. If you want to express this as a function, you could probably say maybe like n squared plus log n. Yeah, so what is the runtime of finding and removing the fifth element from a linked list? Yeah, because it's always the fifth position, right? Yeah. And what if in the middle of that remove operation we swapped two integers exactly 100,000 times? What is the runtime now?
Still over 1.
Yeah, good. Because it's still essentially this constant, right? So what is the runtime of running merge sort 4 times? Yep. And then how about n times? Yeah. Great. So now I suppose we can, yeah. So this is trees, searching and sorting. Okay, for searching and sorting, you should be able to know, you should know the best expected and the worst case time for each of the sorting algorithms, as well as the space complexities. You should know the basic code for the algorithms, and that's kind of given to you on the study guide, so you should just refer to that. You should know the invariants for each of these sorts. And so this is just a table of the time and space complexities. So for selection sort, the time complexity is always n squared. Whereas for insertion sort, you can actually have, in the best case, you can have it run in linear time. You should definitely know all the time complexities and the space complexities for merge sort and quick sort. So merge sort will always run in n log n time, regardless of best, worst, expected. Whereas its space complexity is O of n due to the arrays created with each merge step. For quick sort, well, the runtime actually depends on the pivot, because the pivot determines like essentially your depth of recursion, right? And so if we are able to choose like a pivot that will always essentially bubble up to near like the middle, then we will be able to reduce our time complexities to n log n. Whereas it might be the case that the pivot each time is, say, like the first element, and then your time complexity would run in O(n) squared. As for space complexity, this is just the depth of recursion. So with our optimization, you're able to reduce the depth of recursion to log n. So the space complexity is just O log n. As for heap sort is also just always n log n. We should also take notes of the stabilities. And you can recall that the stability is basically that duplicate elements in the original list retain the same relative order. So if you're sorting this B array, you want the first 5 to always be before this red 5, right? As for an example question, you should be able to give like a high-level pseudocode rendition of merge sorts, assuming you are given the merge algorithm. Yes. So this is essentially just the pseudocode. Yeah, I'll leave that to you to review. We will move on to trees. So trees. So this is a data structure with nodes, sort of like graphs or linked lists. But here, each node has 0 or more children and has exactly 1 parent. There's also a binary tree where each node has at most 2 children. So trees are very useful because it's very natural to write recursive algorithms on trees. Essentially, each recursive method called on a tree fits the formula of basically, say, processing the roots, and then calling the recursive method on the left and right binary trees. And you should know the traversals, the tree traversals. So for pre-order, it's you do the root first, and then you do the left and then the right. And in order, you do the left, then you move up to the root, and then you finish off with the right. And the pattern continues with post, so the left, right, and then do the root last. So essentially, you can just memorize this by seeing where the root is in all of these orders. And one common question you might encounter is, we might give you like an in-order traversal of a tree, and then we'll also give you a pre and post-order traversal along with it. And from that, you are able to perfectly reconstruct the tree. And that's just utilizing basically the definition of these traversals. You can basically deduce the structure. Expression trees. So here, your entire tree basically represents your expression, right? And then nodes will represent operations or values. Your leaves will be your values, whereas other nodes will be operations on these values. And you can see that an in-order traversal of an expression tree is basically how we naturally write like these binary operators. So it would be like 2 plus 3, right? So we start with the left, 2, and then the operation plus, and then the right subtree 3. Yes. We also have binary search trees. And so the invariant on this is that it maintains a certain order, right? So the left subtree of your binary search tree should always be less than your roots, and your right subtree should be greater than. And this is supposing there are no duplicate elements. So this structure is pretty good for facilitating binary search because you can think of this as like a decision tree, right? You start at each node and then you can just make a decision on where to move based on your comparison. And so as long as this is balanced, the height of this tree will essentially just be log n, where n is the number of nodes. And so your search complexity will also run in O log n. Okay. Heaps. So this is also a tree structure which we use to implement priority queues. So a priority queue is essentially just the abstract data type where you're basically maintaining a queue of items that are ordered by their priorities. And so we can have a max or min heap. Essentially, the priority, the max, the priority you process first is either the max or min. And so the invariance we want to enforce on a heap to be able to implement this priority queue is essentially we want the heap to follow heap order, which basically means that every child is essentially less than the roots. And it doesn't really matter. So like I can swap these two subtrees and this will still be correct. This will still maintain the heap order, but it could violate what we call completeness, which is basically, so the order of filling this tree, right? So we want to fill up the left first and then go up to the right. Yeah, the order of filling is basically completeness. As for operations on a heap, inserting, updating, and removing all run in log n time because you're bubbling up or bubbling down on this heap. And that will just run in the height of the tree. And since it's always complete, this should be in the order of log n. For peaking, you can just get your root. So that's constant time. Yeah, so just to review how the operations work. So for inserting an element 0, we first insert the element we want to add to the next position to maintain completeness. So here we would add it under 99 and then we would bubble up. For removing, we take off the root node and then we replace the last elements in our completeness order, essentially, move it up to the root, and then bubble down accordingly. As for representing heaps, if you recall in lecture, we did this with the use of an array. And there was a pretty nifty like index transformation to be able to get like the children. Yes. Moving on to hashing. Okay. So the ideas with hashing is, well, we note that with like, say, an array that's contiguous in memory, we can access an element in constant time because we can just traverse to the index, the memory location associated with the index, right? And so we want to extend this to maps where we have keys and values. So for a key of any type, we want to be able to retrieve the value in constant time. And so to do that, the idea is to essentially convert your key to an index on an array. And to do that, we make use of a hash function that will do this conversion. And then we will mod this by the length of the array to actually get the index. Yes. So there are two ways of approaching hashing. That is with chaining and probing. So for chaining, we're essentially basically just storing a linked list at each bucket. And to retrieve any element, we'll just keep on traversing the linked list until we find the key we're looking for, essentially. For probing, the idea is that each bucket will only contain one element, but if we reach a collision, then we're gonna hop over to like the next bucket and keep on doing this until we can find like either the element we're looking for, or if we're inserting like a null buckets. So yes, and the efficiency of our hash map is contingent upon essentially like the load factor, which you can think of as, say, like how dense your hash map is, right? How many elements per bucket on average is in our hash map. And so past a certain threshold, we want to be able to resize, at least, yeah, we want to be able to rehash, essentially resize to be able to, again, lower this load factor so we can have basically constant time access. And even though this resizing will run in linear time, this is basically amortized. So essentially, if I just resize everything now, the cost of this resize is distributed across all the constant time accesses I will get later on. Another thing to consider is conflict resolution. So if I want to add an element, for example, and I hash it to some bucket, and I see that this bucket already has some entry in it, well, for chaining, I can just attach it to the end of the chain, which is pretty simple. For probing, however, if I have a collision, then I want to be able to keep on hopping over until I find like a null bucket that I can place it into. And then one other thing to note with probing is that when you're removing, if you're removing an entry, you don't necessarily want to replace the removed entry with a null, because that can influence like how you probe later on, right? So if I replace this with null, my probe might terminate early later on for elements beyond it. And so usually we use something like a tombstone, like the NP stuff, to basically just mark that we've removed it instead of just replacing with null. Why we need to? So I guess consider this like hash map with probing, right? So say I have a key that's stored at this last element, but it hashes to this middle element here. Does that make sense so far? Right? And so if I remove this element here between the middle and the last and replace it with a null, later on when I try to find my original last element, I'm gonna hash here, and then I'm gonna hop over to this, but now since this is null, I'm gonna terminate early, right? Even though the entry is here.
So basically, like when you're probing, like if you notice there's a null, you'll think, yeah, I haven't rolled this place before. So there won't be anything else like after this, like because each time you're moving one block. So if you turn into null, like you won't look for the further stuff. So if you remove this original like probed place with a null, you have this chance to like just ignore what's after it. So you don't know like if there are actual elements after this thing. But if you replace it with some mark, like NP, then like wow, I still have things to look afterwards so that you won't miss anything. That's basically that.
Where we time out from the
So I guess this might be a better example. So say like New York, South Carolina, and Virginia all hash to index 3, right?
Yeah.
And so with probing, this is how like the entries will be distributed in our hash map. So say now I actually remove South Carolina and replace it with a null. And so now I'm terminating early when in my search, right? Or sorry, say I then search for Virginia. I start at 3, I hop over, and then I see a null.
I thought it was over.
Yeah, and now it terminates early, even though, well, Virginia might actually be beyond this null points.
Oh.
Yeah, that is why you need tombstones. Big graphs.
Yeah. So I'll introduce you first with several like different graphs. The first one is DAG. So what DAG is directly like isolate graphs. So this example, you can see like there's no cycles in it. And what we can do with DAG is topological sorting. So we repeat the process of like choosing the node with in degree 0. So this is the process. Okay. And then like just move on to the second kind. So bipartite graphs. So usually like I chose the one like arranged in a different way. Usually it's just one side and the other. And you can see like the pointers just points between them, but not inside each set. So in this kind of node, it can be partitioned into 2 sets such that no edges connect 2 nodes in the same set. So I can color them totally differently between each edge. And so the third kind is the planar graphs. So the planar graphs is essentially like you can draw this without the edge crossing. And so the first one is a planar graph. Can anyone like tell me like the reason why it is?
Because we can just remove A to the outside, so just
So you can just drag them to the outside, so that won't cross. Yeah. But for the second, the third one, they are the ones that must have their edge crossing. And there's an interesting like thing about the planar graph is that this allows you to 4-color a graph. So it's similar to map in real world. We can always like 4-color them. But it's not required in our course to like remember all those. So now let's introduce BMFS and DFS. There are several questions I want you to consider, like that's important for like distinguish between those 2 different search methods. So the first one, starting from node A, run BFS and DFS to find node Z. So node Z is not in here, but I just want you to find node Z. So what is the order in which nodes were processed? And can someone like give me like the procedure that you think? So what is the BFS in this graph? I will just order the alphabet like in alphabetic order for like the similar neighbors. So the first one,
the first one I think for BFS is kind of like level order, right?
yes, level
So
order.
It's just the AB, yeah.
Yes, good.
Yeah.
And for DFS, are there thoughts? Like just tell me what's the order. Yeah, good. And so now we kind of know what's the difference between like DFS and BFS now. And so what algorithm would be better to use if our graphs were near infinite and a node was nearby? Yes. Because if it is a DFS, then you'll just go through one path to the infinite. No other ways to help it. So what is the distrap mode? Like more like DFS or BFS? Oh, yeah. And why? Yes. So if you want to search for the like the most nearest way for approaching a node, you will just level search them. That's the best way that you can get. And what in this graph, will topological sort work in this graph? The reason? Yes, because they're cycles. Yeah, good. And so now we're considering like the data structure and efficiency. So for DFS, we make use of a stack. And there's one like practice in our like coding assignments. So it's a natural recursive implementation of a call stack. So usually like for the DFS, we have the recursive call when we're implementing it, and that's a natural stack. Okay. And BFS makes use of a queue. And for efficiency, so we have 2 choices, adjacency list and adjacency matrix. So for adjacency list, it's O of E. How many edges do we have? And for matrix, it's how many, like a square of the number of nodes we have. So I believe like memorize this. And remember, like when you want to choose a specific, so we can choose whether to implement in list or matrix based on how dense the original graph is. Yeah. Okay, so we can run through a depth first search now. Okay, so basically we start, okay, this is easy for you guys now, and we can just go through this. Okay. Okay, this is a good question. So suppose n nodes are reachable among like the E edges. What is the worst case execution and worst case space for DFS in this case? Okay, I can give you the answer and you can think of it like afterwards. So the worst case execution, so time complexity, is O of V plus E. So number of nodes plus the number of edges. And the worst case space is O of V. So because DFS, you just go through every nodes, and at most you can spend is the number of nodes, the most layers you can have. All right. So there are several ways that you'll be tested. Like some example would be instead of like we have this visited, maybe you can use something else to track whether the node has been visited. And also like in this pseudocode, we actually didn't give you like what kind of structure we implement this. So you might be able to like wrote the structure by yourself. And for breadth first search, similarly, like this is the implementation of a queue. And the level order traversal is what you have just been tested, like asked for. So now we go to the shortest path for Dijkstra's algorithm. So there are like some recommended practice for Dijkstra. So you have to memorize the three-part invariant. So the frontier, the settled, and far off sets, and between like each iteration, what do they do? How do they go through this process? And also like you should be able to like actually fill in the tables by yourself, like through several multiple, like I can see there's a question that might have like some procedure hanging at half, and you have to follow the procedure afterwards. And this is, so Dijkstra's algorithm is the ones that like, if you know, then like it's pretty easy. Like you're able to understand and fill up the graphs by yourself, but you have to make sure you understand this whole process. Okay. And then like we move to the spanning tree, and the spanning tree is this kind of graph, which have three properties as we list. So the number of edges, it's the number of nodes minus one. And this graph is fully connected, and also you have node cycles. And so this three property, so any two of them can imply the third one. It's just a fun fact. But remember that the spanning tree have this kind of property. And the reason why we have spanning tree is because we have the two kind of methods for Prim's and also Kruskal algorithm. So here, like I have a fully connected under-directed graph on the right up corner, and there are several spanning tree that can form. Just as like the below two, they're all like valid. Okay, so we can see like this middle and the bottom one have two different properties. So it's the maximum set of edges that contain no cycle and minimum set of edges that connect all vertices. So those are two properties that are also like in the spanning tree. Okay, so now let's go through the two like different approaches for finding the minimum spanning tree. Before that, okay, so for these two properties, we have two ways for finding them. So the first one, to find the max set with no cycles, is you can have this full connected graph at first, and then like you just delete edges from them. And this will require you to delete this edges minus the vertices minus one edges. So usually this would be a lot if you like start with a fully connected graph. So I would recommend you to use adding like from like 0 to add nodes from 0 edges. And those are just what Kroskal and Prim says. So the Kroskal algorithm for selecting the minimum spanning tree is that like every time start from 0, you add the minimum weight edges that connects the two unconnected components. Okay. And for prims, it's just add the edge of a minimum weight that has exactly one endpoint in a node spanning tree. So what we have to know about the spanning trees is basically this 3 property. So when an undirected graph is a tree, and the 3 definitions that I previously said about this spanning tree, and also the Kroskal and the Prim's algorithms. Oh, that's a good question. I think for this one, what I want to add is, what I want to say is to add the minimum weight edge that won't form a cycle. Yes, and for this one, it's the minimum weight that extends from the known tree to the other set. Is that clear?
So we're going to use union find for Kroskal, and union find is not necessary for prims, right?
Union find for Kroskal. Yes, so that's the logic for union find is similar to the Kroskals.
Oh, yeah.
Yeah.
Union find already find.
No, yeah. And so at last, I will just talk something about the greedy algorithm. So basically, I think on the previous, when we're finding something minimum, we're using the idea of greedy. But there are just some facts about greedy algorithm that won't work. So here, for example, this one, yeah, you have 3 different kinds of coins, 7, 5, and 1. Use as few coins as possible to form 10 cents. So in this, we can like very much see that if we use greedy to choose the biggest coin, we'll choose 7111, which is 4. But optimized, we can choose 55, that's only 2. So using greedy won't work here. And in general, like greedy doesn't work a lot. And just as this, so you're just finding the local maximum instead of looking at the global ones. But in Prims and Kroskal, we have proved that this works in graphs for Prims for finding a minimum spanning tree, and so you are able to use them without like other considerations. Basically, this wraps up for our final review session, and just refers to the study guide, and those are pretty clear on what they're like, what topics they cover, and we're like free for like any questions for now.